Hi, in this video, I will introduce our project on hallucination detection for audio language models. Audio language models perform tasks like text-to-audio retrieval, audio captioning, and question answering using paired audio-text data. However, this model often generates responses that seems plausible but are inaccurate or unsupported by the audios, a phenomenon called hallucination, which affect their reliability in critical application. The audio entailment task evaluates whether a hypothesis aligns with an audio premise, with the outcome classified as entailment, neutral, and contradiction. You can see the example in the slide to see the difference. Existing work achieved 83% accuracy with MS-CLAP 2023, but still struggles with hallucination detection. We extended previous efforts by re-implementing the MLP-based classifier for hallucination detection, proposing a new architecture with advanced encoders and classifiers, and also introduced a novel metric to better quantify a hallucination and improve model reliability. We use Closer's entailment dataset, which includes about 5,000 audio recordings. All the audio's description were human annotated, and the hypothesis for entailment, neutral, and contradiction classes were generated using large language models and validated by human annotators. Now comes to our model part. We have a high-level view of the model architecture. The input consists of audio data and corresponding captions. These inputs are passed into the embedding layers, which leverage pre-trained audio language models such as CLAP 2022 and CLAP 2023 from Microsoft and LineClap to extract feature embedding vectors. These vectors then flow through a sequence of 6 processing blocks, each containing linear transformations, batch normalization, activation functions, and dropout layers to enhance robustness. Finally, the processed features are passed through the final layers to generate the output, which provides both a probability prediction and a confidence scores. The detailed calculation of the confidence score will be shown in the next slide. This architecture enables the model to effectively learn and make reliable prediction.
We would also like to propose a new metric for hallucination detection. While previous papers have simply referred to a classification, we believe deeper insight is required to observe model behaviors such as how severe does the model hallucinate. So let Z represent the logits for a single input, where C is the number of classes. In our case, because we classify into neutral, contradictory, or entailment, C would be 3. We softmax the logits to derive them into probabilities, each being P. From the output probabilities, we find the top two, P1 and P2 respectively. We can obtain margin by finding the difference between P1 and P2, and we can obtain the entropy with all of the probabilities on the following math formulation. We use two weights and leverage a normalized margin and entropy to obtain detection confidence. Here we provide experimental results. To train the classifier models, we use the Clodo entailment dataset. This dataset was extended from Clodo audio dataset, leveraging LLMs to generate different language prompts for each audio, labeled in neutral, entailment, or contradiction. Here are the metrics we use to evaluate our hallucination detector model. We use traditional evaluation metrics such as accuracy, precision, recall, and F1. We also use detection confidence, the new proposed metric. Here's the experimental table for classifiers. The baseline is a simple linear layer classifier. We trained and evaluated the classifiers using Clodo dataset, and notably, our proposed model has reached the best scores in the 4 traditional metrics. Thus, when adhering to classification models for hallucination detection, we believe our architecture should be used to achieve high accuracy. Here, we provide analysis of each ALMs using our newly proposed metric detection confidence. With DC, we can observe that some models make severe hallucinations when contradict DC is high, and some models make accurate language descriptions when DC is high in entailment. This metric provides a deeper insight to different model behaviors. For discussion, we see an improvement and limitations of our method. For improvements, made a hallucination detector that leverages ALM models with ensemble approach for precise detection. And we suggested a novel metric that utilized predicted logits to look into the degree of hallucination. However, architecture is relatively large and complex, and the metric requires hyperparameters. In conclusion, we could propose a hallucination detector with a good performance, and we could bring a new metric, detection confidence.